The effect of a force. A force is a push or a pull acting on an object. An unbalanced force will cause the object to accelerate in the direction of that force. An unbalanced force can change an object's shape, start an object moving, stop a moving object, change an object's direction. If the forces acting on an object are balanced, they will have no effect on the movement of the object. A duck on water will experience two forces. The earth pulls down on the duck. This is the weight. The water pushes up on the duck. This is the upthrust. These two forces are equal in size, but act in opposite directions. We say that the forces are balanced. It is possible for a moving object to experience balanced forces. In a submarine, its engines produce a thrust that drives the submarine forward. Water resistance opposes the motion. The two forces balance, and the submarine moves forward at a constant speed. The upthrust of the water balances its weight, allowing the submarine to move forward at a constant depth. Unbalanced forces. If the forces acting on an object do not cancel each other out, an unbalanced or resultant force will act on the object. An object that is stationary will begin to move in the direction of the force. An object moving in the direction of the force will speed up. An object moving in the opposite direction to the force will slow down. If the size of the unbalanced force is increased, the object will speed up or slow down more quickly. As a rocket burns fuel, its weight will reduce. The thrust produced by its engines remains constant. The resultant upward force on the rocket will increase, causing its acceleration to increase. The speed of an object is a measurement of how quickly the object is moving. Speed is the distance travelled by an object in 1 second. The cyclist has travelled 3 meters in 1 second. His speed is therefore 3 meters per second. We can calculate the speed of an object by timing how long it takes to pass between 2 points. To time a moving object, we use a stopwatch. As the car passes the first marker, the stopwatch is started. The stopwatch is stopped as the car passes the second marker. The car has travelled 12 meters in 1.5 seconds. The speed of the car can be calculated using the equation speed equals distance divided by time. Speed equals 12 meters divided by 1.5 seconds, which equals 8 meters per second. Distance time graphs. We can represent the journey of a moving object by a distance time graph. Car A is travelling at a constant speed. It will travel equal distances in equal time intervals. Here the car travels 10 meters every 2 seconds. Its speed is 10 meters divided by 2 seconds, which equals 5 meters per second. A graph of distance against time is a straight line that passes through the origin. The speed of the car can be calculated from the gradient of the graph. Speed equals distance travelled divided by time taken. Speed equals 100 meters divided by 20 seconds, which equals 5 meters per second. The graph above shows the distance moved by a car that is not travelling at a constant speed. The car is decelerating and then stops in a time of 10 seconds. The steepness or gradient of the curve is decreasing, showing that the car is decelerating. The car covers smaller distances each successive second. Speed time graphs. The animation shows a car travelling at a constant speed of 10 meters per second. The graph of the motion is a horizontal straight line parallel to the time axis. At each 2-second interval, the car travels 20 meters. The distance travelled is given by the area under the speed time graph. In 20 seconds, the total distance travelled will be 10 meters per second times 20 seconds, which equals 200 meters. The total distance travelled equals the total area under the speed time graph. Speed and velocity. Speed is a scalar quantity. This means that speed only has size, magnitude. A hammer thrower is rotating the hammer at a constant speed. Velocity is the vector quantity. This means that velocity has both size, magnitude, and direction. We define velocity as the change in distance in unit time in a specific direction. The hammer is continually changing direction. Its velocity is continually changing, although its speed is constant. If the thrower releases the hammer, it will carry on moving in the direction it was moving at the point of release. When an unbalanced force acts on an object, it will accelerate. Acceleration is the change in velocity in unit time. Constant acceleration. The racing car starts from rest and has a constant acceleration of 4 meters per second squared. The velocity time graph will show a straight line passing through the origin. This means that the velocity of the car increases by 4 meters per second each second. Calculating acceleration. The acceleration of the car can be calculated from the equation acceleration equals change in velocity divided by time, which equals 20 meters per second divided by 5 seconds, which equals 4 meters per second squared. Notice that this is equal to the gradient of the velocity time graph. If the acceleration of the racing car is doubled to 8 meters per second squared, the graph will be twice as steep. Distance travelled. When a racing car accelerates, the distance travelled is again given by the area under the graph. In the first second, the car travels 2 meters. The distance travelled can be calculated as the area of the triangle shown on the graph. Distance travelled equals half times 4 meters per second times 1 second, which equals 2 meters. In the next second of motion, the car travels 6 meters. The distance travelled can be found by calculating the area of the triangle and the rectangle as shown. The area of the triangle is still 2 meters. The area of the rectangle is 4 meters per second times 1 second, which equals 4 meters. The total distance travelled in this second is therefore 2 meters plus 4 meters, which equals 6 meters. In the third second, the car travels 10 meters. In the fourth second, the distance travelled is 14 meters. Non-constant acceleration, the free fall of a skydiver. As soon as a skydiver dives out of the helicopter, they begin to accelerate downwards. The earth attracts the skydiver with a force equal to their weight. The skydiver experiences a resultant downward force. As they gain speed through the air, the size of the air resistance force increases. The resultant downward accelerating force decreases, causing their acceleration to decrease. The velocity of the skydiver is continually increasing. Eventually, the air resistance becomes equal to the weight. The two forces balance. The skydiver experiences a zero resultant force and stops accelerating. The skydiver continues to fall with a constant or terminal velocity. The skydiver now opens his parachute. The parachute has a large surface area and exerts a large air resistance force on the skydiver. The skydiver now experiences a resultant decelerating force opposing their motion downwards. This force decreases as the skydiver slows down. Eventually, the air resistance force becomes equal to the weight again. The skydiver now falls with a new and much lower terminal velocity. Forces, mass and acceleration. If an object is subjected to an unbalanced force, it will accelerate in the direction of the force. The magnitude of this acceleration is dependent on the size of the resultant force. As the speed of a car increases, the frictional drag force will also increase. This means that the driving force of the engine must also increase to keep the resultant force constant. If the magnitude of the resultant force acting on the car is doubled, its acceleration will also double. Acceleration is also dependent on mass of an object. For example, the greater the mass of a car, the smaller the acceleration. If the mass of the car is doubled, its acceleration will halve. The resultant force acting on an object, its mass, and its acceleration are all related by the equation resultant force, newtons, equals mass, kilograms, times acceleration, meters per second squared. A memory triangle can be used as an aid when solving problems using this equation. As we have seen, the acceleration of car B is 2 meters per second squared, produced by a resultant force of 3,200 newtons. The mass of the car and passengers can be calculated from mass equals resultant force divided by acceleration, which equals 3,200 newtons divided by 2 meters per second squared, which equals 1,600 kilograms. Stopping distances. A moving car will require a certain distance to be brought to rest. This is called its stopping distance. The distance travelled is made up of 2 parts, the thinking distance and the braking distance. Thinking and braking distances. The thinking distance is the distance travelled by the car before the driver applies the brakes. The braking distance is the distance travelled by the car while the brakes are applied. Both the thinking distance and the braking distance increase greatly as the speed of the car increases. At higher speeds, a car will travel further before the driver applies the brakes. The faster the car, the greater its kinetic energy. This means more work will need to be done by the braking system to bring the car to rest. The figures shown above are taken from the highway code. They illustrate the average thinking and braking distances of a car. Adverse conditions. The stopping distances issued by the highway code are typical for a well-maintained vehicle on a good road surface with an alert driver. However, thinking and braking distances can be greatly affected by a range of adverse conditions. Newton's third law. When 2 objects interact, the forces they exert on each other are equal in magnitude and act in opposite directions. For example, the weight of a cup acts downwards on a table. The table exerts an equal reaction force upwards on the cup. The cup experiences 2 forces, its weight and the reaction force of the table. These 2 forces balance and the cup does not move. If you remove the table, the cup falls. The rocket. Inside the combustion chamber of a rocket, fuel is burned. The combustion produces hot expanding gases that are forced out of the exhaust nozzle of the rocket. The gases exert an equal and opposite force on the rocket. This is the thrust that drives the rocket forward. The gun and projectile. When the gun is fired, a chemical explosion forces the bullet out of the barrel. An equal force and an opposite force act on the gun. This causes the gun to recoil backwards violently.